please welcome Jim Cheetham.
All right, thank you very much, guys. We're in an open developers mini-conf, and I'm not a developer. I get to sit back in a nice, comfortable office and put my head in my palms on a constant basis going, why did you do that? And put it live on the internet. That's fun. I wish they'd ask us first, but they don't. So that's just the abstract that I put up on the talk earlier. Random numbers are used all over the place, mostly crypto failures. So I was just going to go a quick run through some of the stuff about them that I knew, a whole bunch of stuff about them that I didn't know, and listening to quite a lot of people around this conference, there's a fair number that know a damn sight more about this subject than I do in their particular detail, but I'm trying to cover it wide and not go too fast as well. So I'll just pace myself. So there's an awful lot of jargon hanging around the subject. Randomness, from where we're looking at it in computer science, is supposed to say that the next number that turns up is unpredictable, that there is no pattern to the way that the numbers turn up. And you can apply the same thing when you're looking at the output from a hash. A hash has got to widely spread its output across the whole range that's possible. And you get pretty much the same thing, that there's no discernible patterns if it's doing it properly. Although hashes, of course, are quite predictable. A pseudo-random generator is going to produce something which doesn't have a discernible pattern when you look at the output. But of course, like the hashes, it must be completely predictable at some point. And nearly all of them hang off the fact that it's the seed at the beginning that's the thing that helps you generate. We'll cover that in a little bit more detail. And then we have the cryptographically secure pseudo-random number generators, which they say, it's fine. It's all software-based, it's predictable, it's fantastic, but the seeds, you have to look after them. But once you've got that, you can use this for looking after other people's money, especially people that are bigger and nastier than you. The word entropy comes from the thermodynamics. It's a lovely concept about how eventually the universe is going to end up in a state where it can't actually do any work. It might have an energy level, but that energy level is of no use to you whatsoever. So from the thermodynamic perspective, entropy is the thing that's useless to you. I learned the laws of thermodynamics in a slightly different manner to that one, but I like that. We're talking about you can't break even, because you can't tell the difference between what's good and what's bad. When we switch over to using the word entropy in computer science, we're talking about, again, this unpredictability thing, the fact that you will know what state this variable is going to be in the future. If you know that, it doesn't have an awful lot of entropy. If you don't know what state it's going to be in the future, what the next iteration will be, then we're great, we have some entropy here. We measure it in bits, and the example there is the fair coin toss. Toss a coin, you've got 1 bit of entropy. You don't know what's going on because we don't know how the real world works. We have a go. And there is an example of predictability. English text itself has this pretty variable level of entropy in there because we know an awful lot about the structure of the language and what is likely to happen next. So we use the example of English because I'm speaking English. I'm sure a switched language will be saying in Mari there are no Zs in the first place, so that's going to be a big surprise if one of those turns up. So there, just a quick reminder, when you're sitting there in a programming language, there's going to be a function that says on the tin, this returns random numbers. They're pretty easy to work. Most of them are just going to say, if you just call it, you're going to get something between 0 and 1 as a float or whatever. If you stick a range in, like say random 6, you'll get between 1 and 6. Every now and again, you're exposed to a little bit of documentation that suggests to you that you should seed your random number generator before you start the program, as the program starts. Some people believe that they should try and seed the random number generator every single time that they use it. This is not very helpful. It takes a lot of resource. It becomes very predictable. And of course, the problem is that we've got to know where the seeds come from. The seed itself to a good pseudo-random number generator should have been chosen randomly in the first place. So you get a little bit of a bootstrap problem if that's all you've got. And the other one that's always good to know about your random number generators, and there's lots and lots of different variations on the theme, which we'll hit a couple later on, is they've all got a period. They will all repeat at some point in time. If you're churning through the numbers and number 7 was your second output, eventually you'll get yourself to a state where number 7 comes out again, which is good because it's a random number generator, but this time it was 7 followed by, oh, we were followed by 9 the first time around, now we're followed by 9 again. In fact, the whole sequence has started to repeat again. Now the sequences in good generators are very, very big, but it means you can't just turn this thing on and stay up for 2 or 3 years running data through it, because it's going to start repeating. When it starts repeating, that's when the attackers notice what's going on. And as soon as they say, hang on, I saw this sequence of numbers last year, in fact, we've just generated the same sequence now, you've gone round, you've looped. I now know exactly every single random number that you're ever going to come out with from this run of the software, which is fine if you're not using it for crypto. Somebody's heard of Randu? No? We'll hit him in a minute. He's a very good example of something else that's wrong with them. Your pseudo-random number generators have problems with how they distribute across the space of numbers. Some of them have worse problems than others. So the IBM System 360, like late 60s, early 70s, they came out with a random number generator that worked particularly well on their architecture. It involved multiplying a few numbers together that just happened to fit quite well and run quite fast, and they could build special hardware for it. And all the numbers looked like they were random as they were coming out of the system, but there was a few interesting problems with them. Yeah, it didn't really explore it far enough before they implemented it. Once they'd implemented it, it was a saleable product, so they stopped exploring it. When it was discovered to be broken, they just made it run faster. Now, this shows pretty much it's not quite maths for you non-mathematicians like I am a non-mathematician. The wee formula in the middle there just says the value j plus 1 is going to be 65539 times value j. Mod the whole lot by 2 to the 31. It's a fast, simple calculation on this limited hardware the machines had at the time. And it's still fundamentally, that's pretty much what a lot of the random number generators do. You're sitting there and you start multiplying numbers together, you get different output from the input numbers. Then you mod it, you take out some of the bits, you put the results back. I found a lovely graphic on the Wikipedia page for Randu. Some guy went off and he generated, 100,002 values, and then he put them into three-dimensional space. So the first 3 values were the first plot in three-dimensional space, and the next 3 values were the next point in three-dimensional space. Any 3 values are incredibly closely related to each other in Randu. They look really unpredictable to a human, as long as you're not trying to plot them on a graph like that. And of course, it doesn't really matter where you could slice which 3 you're looking at any time. Any 3 are related to each other with a very, very short and simple formula, which shows up visually. So we'll just turn the question a wee bit. Here's a sequence of numbers. Does it look random to you? I know it's a leading question, right?
Yes, it does.
It does look random, doesn't it? That's quite nice. So they're all 4 digits. So I could run the generator and we'll find out. This is the output of a nice pseudo-random number generator. Right, you can Google that sequence of numbers and you'll find it on Cloudflare's blog. They're the people that run Hacker News website for them. This was invented in 1240 CE by a Franciscan monk. I have no idea, because I haven't found the original, what on earth he thought he was doing and why he was doing it. But von Neumann decided, this is how we should look. It looks really, really good. Please never, ever, ever use it. It's called the middle square, and it's a really nice indicator of how we get some random numbers. So we're using 4-digit numbers for this example. You take your number, so the value j plus 1 is going to be the square of the previous value. Take your 4-digit number and square it. Now you're either going to get a 7-digit or an 8-digit number. So for the sake of this, we're going to pad it with zeros to make them all 8 digits, and take the middle 4 out. That doesn't sound like maths, does it? It sounds more like string substitution. So we start off with 1, 2, 3, 4 as a seed, we square it, stick a 0 on the front, and take the middle 4 digits. So the next value, 5227. The next value, 3215. Those numbers look pretty random, and they are actually reasonably random, and they don't fail too badly. And there it is implemented in Bash, which I did last night when I really shouldn't have been. I've got a better version now, which this one is fixed assumption that I'm talking about a 4-digit number. I've got another one that just says whatever you input, that's what I'm going to do. And I'm talking about the 10 hash stuff is just because Bash doesn't like leading zeros. It assumes you've gone octal, and then it starts going badly wrong. So basically all we're doing is we're taking the number, we're squaring it, we're making sure it's 8 digits with the leading 0, and we're cutting out those middle 4 characters and returning them the next one. And this thing generates about 200 numbers in 2 seconds. So it's not bad for Bash, really. But the problem with this process is, although it looks plausible, is there's quite a lot of loops in it. It tends to get down to zeros. If the left-hand side, those 2 digits out of the middle 4 you get, have zeros in them, then the thing suddenly dives down till it just starts producing 0 forever. 0 squared is 0. Pad it out to 8 zeros, take the middle 2 zeros. Because they're better than the ones on the end. And right, so it keep going like that. So it's all good fun. I put a bit of seed. If we have 2-digit numbers, we run in. Some of the periods they just loop, so the 0540 comes back to 0540 really quickly. And you can't predict this by just looking at the algorithm. You have to play around with the outputs. So we've had some good ones. The Mersenne twister, which is, look, I cut and paste those hieroglyphs out of Wikipedia. Thanks, guys. Credit where it's due, because I can't type that on this little keyboard. The Mersenne twister pseudo-random number generator is very good. It has an extremely long period. It generates very good quality, well-distributed numbers, and it's bloody fast for a random number generator. But it says, almost the very first thing on the man page is, please don't use this for crypto. Blum Blum Shrub. It's got a great name, hasn't it? 2 guys called Blum, mathematicians. I presume they're related, but I don't know for sure. But again, it's exactly the same pattern as before. It's Vj plus 1 is Vj squared, mod something. And this is the interesting bit. It turns out that if you choose extremely carefully these 2 very, very large primes to mod the whole answer by, and I know what coprime is because I read it on Wikipedia. It turns out that what it means is that the seed value mustn't factor by any of the other values, something like that. But anyway, if you choose your seeds much more carefully than people generally do, you will get a very, very high quality output really slowly. Then we have Julie C. $10 million into RSA. The NSA chose the values of P and Q. It's now a government standard. If you implement FIPS, you have to implement Julie C. You have to use the P and Q values that they told you. If you know one of the values, in theory, it gives you a very good shortcut into predicting the next sequence. There's a lot of money out there. Just a couple of things that aren't random. Process ID is not random, unless you're running OpenBSD, in which case it might be random. But then you are also random for running OpenBSD. I love OpenBSD, so that's why I'm allowed to say that. Time is not random. You might think that you don't know when your program has initiated, but somebody else might know when your program has initiated. And the digits of pi probably are random. As long as nobody knows you're using them, you're fine. If they know you're using them, your entire output is known. You're deterministic completely. They might be random. They're pretty sure they're randomly distributed. Fantastic. So there are random number testers which go out there and attempt to do a whole bunch of tests on the distribution of the numbers you've got and try and find all the things like, does it suddenly slice badly into 15 lines across this 3-dimensional graph? And unfortunately, there are some very well-known, very non-random sequences that pass a lot of these tests. I'm going to go a bit faster because I'm running short on time, I think. I didn't cut and paste the XKCD, but there it is for you. It's a random number. It's a random number generator, right? Strictly speaking, of course, it's meta-type. The random number generator was the person who typed in a 4. Only once. The reason we like the XKCD one is it is guaranteed random. You roll the dice. We can't predict the output of what dice do in the real world. You have to use casino dice, because if you use Dungeons & Dragons dice, the weighting's all wrong, and the 6 will come up more often on a standard D6 because they've drilled out the pips. Teal's got a different weight. The casino dice, they drill them out, they put the material in, it's got the same density, and they keep going from there. And they pretend that they don't go for magnetic fields around the edge of the table and suddenly flip that way. I'm sure they probably do. Well, who knows what they fill it with, right? But there is actually a very large portion of the government that looks at the casinos to make sure that the government is going to get its money. It doesn't care if the casino gets its money, but it wants to know that the government's going to get its money. So they are pretty fair. We want random numbers for science. You can do that off a pre-published table of random numbers. You don't need to generate the damn things for that, because what you're doing is you're really looking for a fair distribution. The security stuff, right? Your password generators, your tokens and the keys and other things we use for. I'm going to have to go faster than this. Your session tokens need to be unique, because you don't want two people at the same session. They mustn't be predictable. They don't actually have to be fairly distributed. They just have to be unpredictable. A Hacker News website used it. They seeded the damn thing with time of day when the software started, and the software very nicely told you on the front of the web page what time it had started. So the guy crashed the site, let it start up again, saw what time it was, looked at his session key and said, well, there's only 60,000 possible seeds they could have used if it was time in milliseconds. So let's try all of them and find out which one gives me my token. Now I know all of them. Now it wasn't an outside hack, it was an ethical hack. So we don't have large numbers of Hacker News accounts. It wouldn't do you any good if you did. If you're sitting on the Linux kernel, then we've got dev-urandom, which is the right place to go to get random numbers if you're not doing crypto. Dev-random is filled up with environmental noise and things that we can measure about the machine itself, like as we came up, how long the device drivers took to initialize, what your disk spins are like, what's coming off the network card. Things that we can't easily predict. Some of them are predictable, but not easily predictable. And hardware random number generators, right, which do real stuff and come back with real things from physics and pump them through to you in parallel. One of the problems with dev-random is, of course, you don't always have hardware. So your environment might not actually be an unpredictable real-world environment, but that's where most of our machines are these days. Also, especially at install time, your machine is well known. It's completely empty. It doesn't have very many measurements yet. It doesn't have much entropy. And that's exactly the time when you're generating those keys, like your host keys for SSH, which are going to live on that machine for the longest period of time. So let it come up, let Debian or whatever nicely generate you a new host key, and then half an hour later, wipe it out and give yourself a new one, for God's sakes. So dev-random is supposed to know how much that's in it, how much noise is in the system, and it won't return data if it thinks that it's got insufficient entropy available for you. Dev-urandom is a pseudo-generator, so it'll just keep going at full speed, so you're fine to use it. RDRAND, we've had a lot of talk about RDRAND because that came out from Snowden. That's the Intel hardware random number generator on chip, and it's amazing. Its design is wonderful. It does an excellent job of collecting very, very high quality entropy and then letting you go and talk to the main chip in order to get it. Everybody was happy with that-ish, vaguely. Apparently Theo at OpenBSD never trusted it, and 10 years ago he was happy implementing it, but he didn't trust anything, right? That's right, and quite right too. FreeBSD, on the other hand, trusted it completely, and they said on the machine, if we have one of these things, we're just going to use it, and that's going to be the sole source. Because we don't have very many resources left. Edward Snowden told everybody there are some backdoors. And of course, there's the one. What we do when we're collecting environmental noise and stuff, these random number generators, is you pick it all up. There could be some bias in there. There could be some environmental. So if you're taking some electrical measurement, there could be a bit of mains going through that. So we take that data, which is individually different, and we shove it through a hash. So the input was nice and random, therefore all the hashes outputs are distributed as evenly as our good randomness was, but in detail, the hashes are very, very different from each other. But what's happening, unfortunately, is if you don't get access to the raw data, you don't know for sure whether it was a lot of entropy going into your hash or not. Somebody else can say, if there are only 15 possible values going in to your hash, you can't necessarily tell when you're looking on, well, 15 you could tell, but the NSA can tell. So for hardware random number generators, we've got one on the Intel, one on the VIA. The Raspberry Pi's got one. Of course, Broadcom is so closed, it's not funny. We have no idea what it does, really. If you want to buy a hardware random number generator, there's been a good one called the Entropy key that's been for sale from the UK for ages. The company seems to vanish and go away. Reading from somebody called Poran, I didn't even catch up with his talk, I didn't know he was giving it. He's been taking the TV cards and pulling RF noise out of that and doing good randomness, very high quality, very fast. We're building one in Dunedin at the moment because I've got a hardware guy who thinks he knows how to handle noise on his circuit board, the 3 or 4. So at the moment we've got 2 different sources going into that. We're going to make that whole thing, you can pull the original data off it, you can get the noise, you can pull it after it's been hashed through AES, you can play with it, you can rewrite the firmware and put it back on yourself. Because if you don't do that, you can't trust it. So, I had far too many slides, I'm sorry.
Yeah, we've got a minute or 2 for questions if somebody wants to ask one.
Could you just show the name of that hardware generator that you mentioned from the UK?
Entropy key. That one sits up there. That's sort of USB key, and it's just got a couple of avalanche diodes at the back and whitens it and gives you high quality numbers. And they're about £25, I think. But there's been a lot of problems with people getting their orders fulfilled. And for a while, the company seemed to completely vanish. Now it's sort of half come back again. And I have heard somebody talk recently saying that they've got access to some of them as an OEM sale. So they may be coming back online again. If you do, that's a good cheap one. But you can't actually open it up and verify it, which is one we're going for is as an open hardware model where you get the whole lot, you can verify it. We don't expect that anybody's going to care except for a couple of hundred people around the world will care, but nobody else will.
Is there a way of, I mean, if you don't trust it,
yep.
then can you make a good, real random number generator yourself? How hard is that?
It's not very difficult. It isn't.
Depends on whether or not you trust, you know the maths.
The maths itself turns out not to be that difficult. You could read around the subject, and the Turbid paper, where's that guy there? Look for that project, because the guy has given a very, very good, readable breakdown of absolutely everything he's done.
Yeah, on the noise from sound card sort of thing, I found a circuit diagram years ago for, I built one of these, right? It's a bunch of crap and a transistor with one of the pins not connected.
Yeah,
and that creates noise in the circuit.
The other one you do is you get it's another good one is you get a diode, you put it backwards, and you take the voltage up to just enough to freak it out, and then it'll freak out every now and again. And it's so unpredictable. So that's a really good noise source, and it's dirt cheap.
Is that the avalanche diode?
Yes, that's the avalanche diode.
I want one just based on the sound of it.
Yeah.
To go with my flux capacity.
Yeah. What you do is you get a big pile of them. You take the one out of the bottom, and you go for it. It's good.
And on that note, I think we'll finish up. Everyone, please thank Jim for his talk on random numbers.